usual time back to the slides here. You can see that I've changed the slides around a little bit at the bottom here. It's the same stuff, and so I've made some modifications. I just left the old slides from week 5, but I think we'll leave those. We're going to hit these ones now. But really what we're talking about today is categories and bins, which is actually quite an unusual title for this. I'm not exactly sure where we left off last time. I'm going to go and I think I might just start some of these slides just to kind of, I'll just go through them again so that you have an idea about what was in them. So first of all, what we're talking about though is we're making tables, and this is what I call the back of the envelope types of calculations, where for instance, when you are doing some kind of a data analytics, let's call it an experiment here, an experiment where you have to analyze your data, you'll have to put your data somewhere, and you're going to put your data into a table, and that's typically because in RStudio, you have to use tables to to organize your data. That's how RStudio works. And so you'll see that when you're working with in fact, even when we looked at some of the data that we were trying out different types of libraries and packages in R, the data came to us in a table-like form. And so tables seem to be the way that things are going to go. And so here is a table that we have in RStudio, where, for instance, we are dealing with the daily rainfall and the other particulate. Some kind of, I wonder if that's like some kind of precipitation or something. Maybe it's pieces inside the precipitation. It's like some kind of pieces that are inside some rainfall liquid. But what I'm saying though is that this is data. And so you have basically a column A and a column B. And so as we are going through doing our analysis, we're going to start thinking about putting our data into types of tables, because when you're working with R, it makes everything so much easier to plot and to work with when you have a table. So I don't know whether you installed this from last time or not. Maybe you did, but we're working with this new table here, which is called, or this new package called Tibble. And Tibble is going to help us to actually organize our data into tables, very much like what you'd see in a spreadsheet. And so let me just take you to Strawberry Fields. No, I'm going to take you to my RStudio, and I'm going to make a new, I don't know if you can see what I'm doing. What I'm doing is I'm creating I'm going to new file, I'm going to R script, and in R scripts, I'm going to actually create, hope you can see what I'm doing on my screen here. But I have this, I'm going to actually write my data, or sorry, write my code into a file here. So I'm going to save my R script now, which is called Untitled1. I'm just going to take any old place and just dump it there. Where can I put this? And you can see what I'm doing. You can't see what I'm doing. I'm trying to find a place where I can save this file, just because it might be important. So hold on to it later. Gosh, I have so many files here that I have so many directories that I have to like maneuver. Such a noise. Okay, I'll just stick it here. So I'm just call this. I'll call this class, or I'll call this. Actually, I'll put this down as a date, 13th of October _ in class, and then you have an idea about where we are in this thing here. So when I save this, you'll see where we are. So I've just given my script a file name. Now the reason why I do that is because if something happens, and for instance, like in this case, when I copy and paste my code, and everything becomes kind of just extraordinary, where nothing seems to, where the formatting has been lost, as what we see typically happens here, then I can still get it back. So anyway, this is what my code is going to look like for my slides. You can verify this by going back to the slides. Make sure that your slides are in actually this order. So on my RStudio, I'm going to go ahead and I'll just install this again just because. Now remember that I'm going to push that run button at the top of my screen. Hopefully you can see me. Maybe that's me pushing it. But it's going to install this thing called Tibble. Do I want to install sources from this package and these compilations? Sure, why not? Just put yes. Okay, it doesn't. I don't think it takes up too much extra time. I wonder if you can all see this. I think you can. Anyway, when you install a package, you have all this stuff that shows up. Don't worry about that stuff. All that stuff that you see at the bottom of the thing here, all this, this is really just the compiler in your machine for that works for R, compiling code that's from C. This is like this is a C. This is a package written in C, or maybe in C++. I'm not sure, but C. You can see that, for instance, attribute C, coerce C, init C. And so what this is doing is just running a compiler. And so while all this is happening here, you might notice that your machine starts to really take off and the fan starts buzzing. That's just because it has to do a lot of extra work. But if everything has gone correctly, then you should have no error messages at the very, very end. It should just finish and be done. Now, next, you're going to go to the library. And oh, by the way, let me just tell you one more thing. Now, once I've installed this, I'm going to put this comment in front of this like that on that line so that I don't keep installing this every time I want to use this code. You only have to install it once. And even then, I think that there's actually a way in RStudio to update all your packages. If you go to if you go to your tools, at least on my RStudio, if I go to tools, you can't see what I'm looking at. But if you go to tools, there's an option there that says check for package updates. You can always run that like every month or so just to see if there's any updates. But otherwise, you won't need this again. Now I'm going to run my Tibble. I'm going to run tidyverse because we need those for this lesson. And hopefully, if everything has gone right in Tibble, I don't see anything coming up. But in tidyverse, I get all this line noise that shows up. Okay, good. So now what we're going to do is we are going to use that library to create, where are we now? To create a data table. So imagine now that we're working on some data and we want to be able to put some information into a data table here so that we can work with it. I'm just going to go ahead and copy this and hopefully I can paste this without making it look like a complete mess. Oh no, so actually the table gets all kind of confused here. Let me just go ahead and kind of reorganize things so that it makes some sense to you. So I have Tibble, which is going to be this first part there. What do I need now? Let me see where I can see. Function Tibble. So I think, oh, you know what? That's not this part. It's going to be Tibble this part. There we go. So I have all this stuff inside here. In fact, if I just go ahead and push this down like that, then this should be what the code looks like. And then you can go back to your actual slides and make sure that it actually looks like that so that it's readable. I don't think that actually that it will not, it should still run. It should still run even if it's confusing, but I put it in this way so that you can see you can see what the table looks like. Otherwise it's just really confusing when you look at the code. So getting back to this thing here now, when I run this code here, you'll see that I have this information that shows up down at the bottom, which is actually our table. It's our data table. One thing I would like to draw your attention to is that notice that over here, columns are labeled on the line like this. So I have column 1 is equal to, and then remember C, this C open and close parentheses. In other words, all the stuff inside here inside C. C is a vector. I always say that it should have been called V as in vector, but C creates a vector or an array. It creates an array in R. And so this array that we have here, A1, B1, C1, D1, that is your array of your first row. And in fact, if you go down to where the table was actually created in column 1 here, you can see that A1, B1, C1, and D1 are the first column. Column 2 is the same way. You can see that this information here all arrived here. And so what I'm saying is that this could potentially upset your result if you made a table that looks like this, and if you're expecting A1, A2, A3, if you're expecting that to be your column, and 14, if you're expecting that to be your column, then it's not going to work. So excuse me here. I was raking the leaves out with my son, and we were breathing in all this dust, and so I'm just kind of like, and it's also allergy season too, but I'm just getting all this allergy stuff. One thing I'm going to do now is, while that's interesting to look at, I'm going to actually create, if I go back over here, I think I can create some of my slides, I'll be able to create a variable and assign all of this stuff to my variable. And so let's see here. Yeah, there we are. I called it sample data. Not very interesting, but you know, so it could be working. It's a working solution. Let's go back here and go back to my R. And if I put sample data, remember I assign it like this. My code looks like this. If I run this, now you'll see that in my global environment, you can see up here, my global environment has sample data. Now, that's a very powerful thing for us because now we can just go ahead and type in view with a capital V, sample data, and I can see what my data looks like. And actually, this is a better way, I claim. It is a better way of actually viewing the data than viewing it on a screen, because as you remember that when we're viewing this on a screen, like if I'm just going up and down like this, then I have to go up and down like this. It's kind of sometimes difficult to kind of see what's going on. But for here though, I like this because when I'm looking at my sample data in this spreadsheet, then I have the ability to, if I'm up here, I can click on these column headers and organize things alphabetically or however I want. And so that's actually quite an important, quite an easy, easy to use tool. Okay, so let's move on back to our slides here. If I can get back to them. It takes me a while to find the slides I'm looking at. Oh yes, one thing I wanted to talk about though is if you look at the slides, you'll see at the bottom here we have sample data, then we have bracket, comma 1. This is actually something that should be very familiar to you because we were doing this work in our test here. So if I type in sample data like this, if I type in this, oops, of course I may have spelled something here. If I type in this, then I get everything. It gives you the whole table. But remember that if I put a 1 here, this is going to give me that row. And if I put in a 1 on the left-hand side, this is the column here. That's the column. And if I do this, this is the row. And I can see that this is the row because just a quick thing that I look for is you can actually, first of all, you can see the column names, and you can see like it's like the headers are at the top here. All right. You can do, I mean, remember you can do some other stuff too if you want. You can actually locate specific things. So if I want the first element from the first row and the first column, then I can just push 1, 1, 1, 2, and you can see that I can actually go after A2. And if you look at the filter, or sorry, the up above here on my table, I can see that A2 is the element from the first row and the second column. And so this is kind of how that would work. Alrighty, so you have that ability now. So I know we've seen this all before, but the reason why I'm actually bringing this up again is because it's important that you know that now you can create your own tables and you can use the same code that you knew how to use from before. So it's all back. It's all there. There we go. Okay, so in fact, I have this information actually in the slides. You can see here. Oops, let me just go back. Finding things here. So you have all this information in the slides that we just covered. So you have notes that you can use. Now let's make another more exhaustive table here, a bigger table. And I was with some friends the other day, and I thought, you know what? I'm going to put everyone's name into a data table. That's not creepy at all. And so what I did was I went in and I just added some names, and you'll see that actually this is kind of a mess as it is now. So I'm going to go ahead and format this thing quickly while I'm doing this. Let's see. We have age. Actually, I'll put this down here. I have age. Sometimes moving things around a little bit so that it's easier to read actually makes all the difference in the world. Because if you don't do that, then sometimes it's hard to kind of remember what each piece is doing. Let me just go ahead and move that back a bit. Oops, too far, too much. Okay, that helps. Okay, so this is my new table. I'm going to go ahead and just run this. Go up here. I can include that because that's a comment. And you'll see that I have my friends table now showing up at the top. And so we have different kinds of information actually in this table. So let me just talk about this for a second, and this will help us to go through the next part of our slides. And that is we have names: Alexander, Luke, Freddie, Sam, Amelia, and Daisy. And we have their ages. Amelia is a little bit young in this one here, so I mean, she's 3 years old. But still, we have the height, and then we have whether they are in college or not. Now, the height is a numerical value. You say it's an integer. And so is the age, it's an integer. But the name and in college is a different type of data entirely. And so when I say it's a different kind of data, you really need to start making a note of the data that you see in your tables here, because you really cannot just graph the in college data or the name data ggplot like we've been doing before. You could use ggplot to graph the age and the height, and that's perfectly acceptable. But for in college or for the names data, it's a text-based data. It's not numerical, and so you have to do some specific things if you want to analyze that. Yes, sir. Yes, so the question is then, so what could we do? And so one of my bright scholars here has said that we could use them for aesthetics. We could use them to actually categorize, ooh, there's that word, categorize some of our points. And so that brings me to actually today's topic of what we're working with today. We are working with the categories. We're going to be using data like the name and the, and perhaps the, you know, whether they're in college or not, we're going to be using this kind of data to facilitate some of our plots that we've been working with before. And so this comes from our chapter 5. And if you're in the book, the printed book, or if you're in the web here, you're on chapter 7. But it takes us into kind of like working with different kinds of data where we're actually going to be categorizing types of data and then plotting them. So let me just tell this story first. But we're really using kind of the visualization techniques. Remember that one of the main pieces in data analytics is the ability to visualize data. That's absolutely fundamental. And the reason for that is because we as people are very, very good at picking out trends and patterns when you look at something graphically. And so we're going to be exploring data, we're going to exploratory, but exploring data using graphics. Again, I mean, a lot of this is about using graphics. And so what we're going to be doing is we're going to be asking ourselves, like, you know, well, how can we actually analyze our data? What can we do to explore this data? In other words, what kind of visualization, I'll just cut to the chase here, but what kinds of visualization can we see which would help to explain some kind of variation between variables? Or how can we, or some kind of covariation? How do we explain how one group of numbers is being influenced by another group of numbers? And as you've probably guessed by now, we're using graphics. Anyway, so let me just get some terms here just before we get to that other stuff, you know, to the graphics and the categories. But when I'm talking about a variable, I'm talking about a quantity, or it's a property or something that you can measure. It's a quantity or quality of something that you can measure. So a variable, if someone says, I looked at the results, and there are many, many variables that we have to understand. So what do they mean by variables? Well, they're just saying that many places where you can actually draw measurements from that study. So variables, you have the independent variable and the dependent variable. If you have like remember the plot that we looked at where we're talking about more study time it gives you better grades. You could say that grades is the dependent variable on the amount of study time. So the more study time you put in, the better your grades get. And so you have these two different things that you are studying. So we call those variables. Now the value is actually what the numerical value would be. What is the worth of that variable? The value of the variable may change from measurement to measurement, but it's something that you can. It's actually what you receive when you do a measurement, when you take a measurement. Now, an observation is a kind of a tuple. It's like a set of information here from one specific reading. So I'll just read this. It's a set of measurements made under similar conditions. We usually make of all measurements in an observation at the same time on the same object. And so you can think of, if you're looking at going back to the more time you spend studying, the better your grades get. You can think of the observations being, in this case, the set of data that comes from a number of different students, you know, a whole bunch of different students. And so I'm saying that I've looked at 10 students. I found out how many hours they studied and what their grades were that they achieved. Those are my observations, my students, and the data points that come from them. And then the tabular data, this is all the information that I'm actually putting inside well, let's read this here. It's a set of values, each associated with a variable and an observation. And so it's, for instance, it's that row of information, I guess you can call it, that exists in the table. So now, what does that have to do with what we were just talking about before with categories? Well, you're going to see that when you collect information, it's not all numerical, but you get categories. And so what is a category? Well, a categorical variable is a variable that can only take on like a limited number of defined states, I guess you'd call it here. It's another number of fixed possible values. So for instance, in this case, This data that we see in this table, nationality, C1, C2, C3, you have French, Italian, German, and other. This is a binary table. And so I'm using categorical variables to define French, Italian, German, and other. And so you'll see in this table for the top row here, French, that if I have 0 for column 1, 0 for column 2, and then 1 for column 3, in other words, 0, 0, 1, that is the code for French. And if I have 1, 0, 0, that's the column for Italian. So what I'm saying is that a categorical variable is a variable that's, in this case, is either 0 or 1, which is binary. But it doesn't mean that that's the only, that you're stuck, that you can't use those variables in some advanced way. And so in this table, I'm using these variables as binary words, if you will, to mark all the different countries. And so actually, if you use these categorical variables in a system like this, then actually you can seemingly, you have as much strength in these as you would for seemingly anything else. It's just that I guess your row would look different. In this case, you have to have 3 different binary numbers here to represent these different nationalities. Okay, so I'm going to, let me just go ahead and do something here. So I'm going to go, so if you talk about these, another categorical variable would be, for instance, like your gender identity. There's male or female. You may have a number that you use for months, like 1 through 12. These are, I mean, they're basically numbers which are established to have defined meanings. 1 through 12 is understood to be January through December. And so this categorical data, as we're talking about now, this is saying that we're working with these variables, which are not like numbers, but we have to, but they can still contain information, but we have to work with them in a different way than how we work with numbers. And so that's really what we're talking about today, is working with categorical types of data sets. Now, this is another thing here. Going back to this diamonds data set that we had before. In fact, I think that I can just go back to this and see this on my screen. But if I type in, for instance, I'll go back here and I just go into view diamonds. I think this will just go, there we are. Diamonds is always going to be one of those things that we have in our data set. If we load tidyverse, we get diamonds. That's not a bad thing to say. We get diamonds and we get tidyverse. So here we are. So if you look at the columns, I'm hoping now that you're looking at your data now with new eyes, a different way of looking at your data. So the first number is carat, which seems to be decimal point numbers. Okay, so that's a number. It's a number, so we can probably plot that with ggplot without having to worry about going out of our way to write new code. But the cut, that I'm concerned about. In fact, if I just organize this by, if I organize the cut by alphabetically here, I can see that I have fair, actually I have, or very good, premium, ideal, very good. What I'm saying is that cut is seemingly one of 5 different values. Either it's premium, ideal, very good, good, and whatever the other one was. Good, I guess, very good. Anyway, it's all in there somewhere. But what I'm saying is that cut, these are actually words. Each variable or each row has one of these 5 words to describe it. Same thing with color. Color is D, F, E, F, E, E. It's like G. It seems like these are predefined meanings. They're just words that have some meaning here. And so again, you can say that all this data, in fact, all the data that we have here is 53,940 entries here. Each of these things has been assigned to either a cut of good or whatever it may be, or very good, and etc. And then we have, it's been defined one of, I guess, a small number of colors. And then the same thing with clarity. So clarity, everything fits into, I think it's like I think there's 8 different forms of clarity or something. I'm not quite sure, that's not true. But anyway, but there's not very many clarities. And so the cut, the color, the clarity, those are all what we call categorical types of variables, because they just have, there's just a few different types of, there's a few members in each of these sets. And so each of these rows is actually, is assigned to one of those members of the set. It's not like carat, where you can have, like, for instance, seemingly any number that you want. like 0.23. In fact, I move all the way down to the, let's just move someplace in the middle here. Let's see what all the numbers are. So 0.71. So we have like a whole variety of numbers for caret. And the same thing is we have a whole variety of numbers for table, for depth, for X, for Y, for Z, for price. We have all these numbers seem to be just kind of just numbers that come as they are. Whereas, for instance, clarity, color, and depth, sorry, not depth, cut, color, and clarity are actually kind of, you know, they're assigned to words which have some meaning. Anyway, so I think that what you're seeing now is that there are different kinds of data. Not everything can be just plotted just easily right off the cuff here. So this is if we're plotting some categorical stuff here, then it's I'll just copy this everything here so I can get this here. But if we're going to be plotting something that has some kind of category, then we have to use some special help here. And so the special help that we'd use is something like down here, where we're using, of course, we have the X and the Y, which is the X and the Y, as you remember from our data, was the, what was that? The X and the Y was, well, those are numbers, but the caret was a floating point. And so we simply had a whole bunch of options here for how we could plot those numbers. But in when you're working with clarity, what is clarity? Well, remember that clarity is this. It's not a number. Clarity was this column here, V, one S1 or something. And so that's kind of difficult to deal with. So anyway, I'm going to go ahead and just copy this. I'm going to dump this into my RStudio, and I think that we can have some fun with this code in just a moment. So let me go back here. And of course, nothing looks like it's what it's supposed to look like. So I have to go through and kind of organize things a little bit. Okay, so that doesn't need to be here. I may as well do everything while I'm working at this. What I'm looking for is, hopefully it's that. Make sure that when you've done this, when you've reorganized your data or your code, that it looks exactly like this. I'm hoping that it does, otherwise it's not going to work. Let's see. I think that'll do fine. Okay, that should work. Okay, so let me go back. And I'm going to run this first piece right here. So it'll take some time on this machine because I have all these things running on here. But we do have a plot which will eventually come up here. And so you can see that this is the hallmark of categorical plotting looks like. Where, for instance, if you can see this, you have a column which is fair. You have a column which is good, very good, premium, and ideal. So you can see that all the data fits in one of these 5 different slots. Each pigeonhole here, if there's 5 pigeonholes here, each point of data fits into one of those pigeonholes. And so that is what we mean by categorical data. It's not continuous where you have like a line that just kind of like sprawls and does whatever it wants to do. Instead, it's either here, or it's here, or it's here, or it's there. It can only be in one place at a time. And that is the nature of category. And so getting back to an earlier question that we had here, which was like, well, how do we plot with these things? Well, you've already done that. You've already done this. You've assigned color to that category. And so now you're saying, I recognize that there are specific categories of my data. And so what can I do to make this thing, to actually include that information too? Well, we can just go ahead and add color. Another thing we can do, for instance, is I'll just put, if I change to size, how does that change my plot? In fact, it might make things a little bit more clumsy looking, but let's see. I would say that color would probably be better. Yeah, color is better for obvious reasons, because when we get down toward the y equals 0.5 and below, we really can't see, the points are so close together that we really can't see the actual individual sizes. I guess what we could always do is we could go back to our code and we put color is also equal to, now this is kind of a faux pas in analytics here, because we're using one category and we're plotting it, with color and size. Maybe that'll help you, but you're kind of wasting one of these attributes. So you're wasting color or you're wasting size because it's on the same attribute, or it's on the same variable. Maybe this is more helpful though, who knows? So you can see that when you're looking at the skewed nature, in fact, this reminds me of a test question that we had where it was asking you to use the color to see how the points were skewed. Well, you can see that the clarity, I'm just going by this. If I'm looking at premium, which is this second from the last column here, you can see that the lighter colors seem to be gathered toward the bottom of my as my y values get smaller. In other words, I see the value if or if. If you see this VVS1, VVS2, VS1, VS2, those clarity categorical elements tend to gather toward the bottom of the premium and the good and the very good. I guess all of them actually. They tend to gather, that's the trend that I see, they tend to gather toward the bottomest. In other words, I see the lighter colors gathering at the bottom. And in general, I see the darker, you probably can't see this from here, but these are darker purple colors. I can see the darker purple or the violet colors gathering toward the top as my y value gets bigger. And so that means that I1, SI2, SI1, those types of values tend to be gathering at the top. And so the trend that I would read in this thing is that as my y gets bigger, my clarity becomes less like IF and more like I1. In other words, it's, you know, the colors are indicating that. So what I'm trying to say though is that, I mean, that's all very interesting in academics to make that assessment. But what I'm actually trying to say though is that just because you're working with categorical variables does not mean that you cannot still use those visually. And so we are actually spending a lot of time in this course visualizing data. And so this is another way of visualizing your information. Let's see by running the next piece here, we're going to generate a histogram. You can use histograms to also plot categorical variables. Here you can see that, for instance, you have fair, good, very good, premium, and ideal. Each of those bars represents a kind of a bin where the values for ideal or for premium or for very good or good or fair, where they have just been dropped. And so you can see how many of those values are inside the ideal bin, or how many, I'll call them bins now, but how many values are inside the premium bin, how many values are there inside the very good bin, or how many values are there in good and fair. And so the histogram is actually how many observations, I guess, are there in each of these ideal, premium, very good, good, fair bins. Now, one thing I'd like to do though is that while I have visuals on here, that's not very helpful to me if I wanted to actually run the numbers. And so what we can do is we can figure out, for instance, I can move this over here. We can actually figure out like what are the actual numbers that make up these bins. And so you'll see that this code that I've just run here, and I'll talk about what this in the middle here means in just a moment. But what I'm doing now is I'm looking at my diamonds data set, and I'm pouring that information into this function here called count cut. Cut, as you remember, the cut is this piece that's right here in this column, very good, or whatever it was, ideal or something. And so we have all that information in there. And so what I'm doing is I'm actually saying, go inside the diamonds data here and count up how many different of each sort of cut there are. So this is actually a quick piece of code that you can write. If you wrote this in Python, it might take you 2 or 3 lines, but here it's just like 1 line. Actually, it's just like seemingly 3 or 4 words. But what it's doing is it says, okay, when I count how many times fair comes up in that column, I get 1,610. If I find out how many times the word good comes up, I get 4,906, and so on and so forth. And so these numbers that we see here are the places where we get the columns. It's where the columns are actually built. And so if you look at ideal, ideal in this over here, this value is 21,551. And in our histogram, you can, I can't select this here, but in the histogram where y is equal to 20,000, you can see that the ideal bar is just over that. And so that's where this value is actually coming from. So what you have in your hands now is actually a very important skill. And that is that you're now able to make a plot of your histogram to get a kind of a visual of what the numbers look like. But you can also get to the numbers yourself if you want them. Because remember, one thing that you need to work with when you're working with analysis is the numbers. And so this is one thing that actually, I'm going to vent for a second here. You guys, you get me all fired up here. But I used to use a Fitbit. I'm not saying that they're bad products or anything like that, but I don't use my Fitbit anymore. probably because it went through the washer and then went through the dryer, and so it didn't survive that. But one thing that used to bother me though was I used to get every month an email from the Fitbit company, which would have all these plots of like how much exercise I did, how far I walked, my heartbeats. What else was there? Some other stuff, a whole bunch of other things, and the graphs just looks just amazing, just absolutely phenomenal. But me being me, I wanted to do my own analysis on these things to see whether, for instance, I was doing much more walking this year, than say last year or say the year before. I mean, am I actually walking more? Am I doing more biking? You know, I wanted to actually do those types of analyses. And I found that I was limited only to the graphs and plots that the Fitbit email provided me. In fact, I didn't have access to my own numbers, so I couldn't actually write my own plots, which was really annoying. And so that's something that used to drive me just berserk. So in other words, while Fitbit gave me this plot here, they gave me the plots that came out of this code, I couldn't actually see the data as numbers. I couldn't do this and actually figure out exactly what was my ideal plot here, what was my premium plot, what was my very good number, what exactly were these values? And so they don't give you that information, which is, I think, a little bit weird. I mean, I would have thought that it's my data. I should actually be able to see those numbers, but anyway. But the washer and dryer decided the fate of how I would continue, and it was actually kind of a sad day. I liked my Fitbit watch, but whatever. I'm going to go back to my slides here. I'm not knocking Fitbit. I'm just saying that I wish that I would have been able to have the data, because it seems like that's the next logical step. Once you're plotting things, you may as well have the data so you can create some of your own plots. Now, I've mentioned the word continuous, but I haven't mentioned the word discrete. So continuous data are numbers that can be, or they're values that can be any value. They are what they are. Wherever they fall, that's the value. Whereas discrete values are numbers which are kind of, they're numbers, but they're still kind of like in a category, if you will. You can see that the plots look slightly different here, where you have continuous, the numbers are kind of meandering and winding all over the place, and everything's, and they just kind of land wherever they want. But discrete, it seems that you're either in this bin or you're this value, unless of course you're greater than some kind of threshold. And if you're greater than a threshold, then you're in the next value. And so the discrete values are categorized by kinds of windows between on the number line. So if you're between this number and that number, then you are this value. However, if you're a number that's bigger and you're in the next window on the number line, then you're categorized as this type of number. And so your graphs are going to look very, very different here. Discrete graphs tend to be very boxy, whereas continuous ones are just meandering. Maybe a better way of pointing this out would be to look at this, where, for instance, discrete data tends to look more kind of like pixelated data. And what that means is that you're either a value that belongs in this cell, or if you're greater than that cell, then you're in the next cell. But you can't be in both cells at the same time. It just doesn't work that way. And so there's a series of rules that define what cell you can be in. Whereas there are no such rules if you are a continuous data point. You just are wherever you are. And so if you think in terms of like just rules or no rules, discrete data has rules where you have to fit inside certain I guess windows on the number line to belong. Whereas in continuous data, you don't have to fit inside specific number line rules to belong. It's kind of like a Minecraft video here. If you're Minecraft data, then you are continuous data, or sorry, you're discrete data. I don't want to place Minecraft in here. I do. I don't mind saying that. Okay, so getting back to this this table that we're looking at here in our diamonds, whereas the continuous data, well, the continuous data, I would say, is the caret data, maybe the depth data, table, price, XYZ. It's those numbers that just kind of like show up as however they are. There's no rule to say that if your number, between 0.5 and 1, then you're this value. If you're less than that than 0.5, then that means you're another value. There's no rule like that. Whereas there is a kind of a set rule, I guess, if you're a word that fits in the category cut or color or clarity. So for instance, in order to land in those categories, there are rules. How do you say that something is ideal and not premium, or is not good, or is very good? How do you say who is who? How do you say who fits in which group? Or for instance, the colors. What kind of rule is there involved in saying that a color is E and not I, or it's I and not J, or so on and so forth? So you have a bunch of things to consider here. And so that's your continuous, these are your continuous types of values. Now, I want to talk about this new piece of code here that we haven't seen before. We've seen some of this other stuff here. This may be slightly new. This is a histogram, where we're actually creating this histogram that we see here. But this new code is called bin width. And so as we were talking about the rules, if you will, that kind of contribute to how a value is placed, you have this code down here called bin width is that rule. And so in other words, you don't actually see this rule, but what it's saying here, and this, I'll just run this, but what it's saying is take all the data and cut it up into chunks here of 0.5 in length, I guess. And so each 0.5 length actually contributes to the histogram bars that you can see here. And so we have 1, 2, 3, 4, 5, 6, 7, I would say. There are 7 bars of data here, and each of those 7 bars, we'll say is a measurement of 0.5, and all of our data that we have must fit inside one of those bars. And so this bin width actually becomes our rule. Now, if I go ahead and change things around a little bit, let's just copy this again. I'm going to say that now it's no longer 0.5, but I'll say it's 0.9. See what happens there. You can see now I get fewer bars. I get 1, 2, 3, 4. So now it's saying that my data has to fit inside 4 different, or the data has to fit inside one of 4 different bars. And you can kind of get an idea that as I make this number smaller, let's change this number to like 0.1, something really small. You can see that I'm getting more and more bars. And so believe it or not, that this data that we see here, that all those spikes there, is actually the same data as this. Everyone see that? Try that out on your thing here. But you see all those little spires and spikes and things you see? That data is the same as this, but it looks different. And so what I'm saying is that just because you have a plot of your data, it doesn't necessarily mean that you're seeing everything. I know this puts everything that we've been talking in this class completely up in the air, and nobody cares about what's going on. But no, it does change everything. It changes things because now you're looking at your data with different types of rules. You're assigning your data points into different bins depending on the width of that bin. And so, I mean, if I look at this data here, if I look at that particular histogram, and then I look at, let's go to the bottom here, 0.1. I look at that histogram, I could be convinced that I'm looking at a different spread of data. I could be convinced. So what I'm trying to say though is that this is where the talent comes from as a data scientist, and that is that you have to kind of ignore the illusion that the bin widths can put out, making you think that you're looking at different data, and remember that you're looking for a pattern. So you're looking to see whether there's some kind of a I don't know, something that's actually measurable. So anyway, getting back to this thing here, so I'm going to go back into my notes. I'm looking at my chat right now. Somebody is saying I should get a Garmin. Thank you, Danielle. I've actually got one, which is I didn't want to mention that, but it's not the most modern thing, but I do have a Garmin. Thank you. Let me think. Where was I again? Okay, so let's go back to the slides and let's see where we're actually located. So what I'm trying to say though is that as you're working with, as you're looking at your data here, be sure to keep keep track of where the data is actually being kind of fitted into the bins here. Now, one thing I promised you, which I haven't gone through, is what does this thing here mean? What does this thing do? Well, you can think of this as kind of like, and then. So every time I see this is a tidyverse thing, And so when you have your data set, you can say, take your data set, and then what am I going to do with it? And then I want you to count the caret groupings. So anytime you see this, in your mind, I want you to start thinking, and then, rather than just parenthesis, or sorry, percentage greater than percentage. That doesn't really mean much. But if you think of that as kind of computer code to mean and then, it will help you to kind of figure out how to work things. This is your piping information. In other words, at the DOS, or not DOS, but the terminal prompt, you use the pipe. This is basically your piping information. You're just taking the information from diamonds and you're carrying it across and you're dumping it into this next thing over here, which does that. And so we have the count. Okay, so another thing I wanted to take you through here, though, is that I'll just go ahead and plot this information here. What I'm doing is I'm taking diamonds, and then I'm going to count the cut width of carat at 0.5. I'll show you what that means here when I paste this in here. But I'm going to kind of start kind of limiting my data points into something that I can actually kind of control. So I'm not just going to say, give me this bin width and see what happens here. I'm actually going to, I'm trying to actually do more control, or have more control of my data. So let me just put this down here. What does this thing here do? So what this is doing now is it's saying here to give me take the diamonds data, and then I want you to count all the data that I have for which the rule of all the carats, it's kind of hard to explain here, but all the carat information is going to be subjected to the rule where it's going to be placed into bins of 0.5, count up how many elements are in each of those bins. So you can see that when I run this, I have my little windows, or my little I guess my window on the time, or on the number line opening here. So I have points, or negative 0.25 to 0.25. That's the whole thing. That's my whole, I guess is that my whole thing? I'm sorry, it's not, it's negative point. These are where the points are actually landing. And then, for instance, I have here from the 0.25 to 0.075, or sorry, 0.75, I'm seeing how many of those points are actually showing up inside this window, or this, if I have this rule. So in other words, take the carat data, cut it up into little chunks here, where each chunk is a length of 0.5. And then tell me how many we have, or tell me how the distributions fall. And so you can see that just by looking, if you turn your head to one side and you look at this, you can see that most of your distribution is showing up in here someplace, which is actually rather important. And actually that does make sense, because going back to the histogram that I see on the right-hand side of my screen, most of my data is actually showing up between the 0 and the 1, and it begins to taper off after that point. So now what I'm going to do is, let's go back to my slides and make sure that I haven't missed anything here, which I might do. Then what I'm going to do is I'm going to plot that. I'll use the ggplot command next and see what my plot would look like. So that's basically this line of code here. I'm going to cross my fingers and it works. And there we are. So this is my spread of my data here, according to my bin width. So if I wanted to change my bin width, let's just say that I'm going to change, I'll just copy this code and do this again. Let's say I'm going to cut up my code, or sorry, cut up my data and put everything to a bin that's maybe length 1.0. What do I get now? You can see that everything there are fewer bins, 1, 2, 3, 4, 5, 6. 6 bins. If I plotted those 6 bins, how would the distribution appear? You get something like this. With 1, 2, 3, 4, 5, and 6, you can't even see them. They're above the 4 and then on the far right-hand side. And you can't see them because you can't really plot one data point on the right-hand side of this plot when you have like 29,000. It seems like the scale is just so uneven that one of these is completely, it just vanishes at the side of the other. So with 30,000 data points over here, you're not going to be able to see the one over there. Anyway, that is a way of cutting up your data though, so you can kind of you can do some analysis and actually get the points and see what your distribution looks like. But this isn't the full story. The full story is that you as a data scientist, you have to do all these kinds of tests to see it's not just plotting anymore, but you're actually asking yourself, what's the best way of plotting? What's the best way of showing something of the actual trends that we're looking for? So another thing I want to show you though is that, for instance, if you run the same code here, if I'm going to take the diamonds data and cut it up into widths of 0.5, I'm going to cut the carat data into widths of 0.5. if I run that data, I can see that this number here in the orange box on the right-hand side, 29,498, that number actually appears in our histogram, which is the tallest bar. So I'm trying to make the case here that you now have access to actual visuals, but also if you want the numbers that give you those visuals, then you have the code to do that. The only thing that's different here, the information is the same. The only thing that's different is that one, the output is given to you in the form of a plot, and the other one, the output is given to you in the form of numbers. And so now you have the ability to kind of like look at both sides of the coin and to do your work. Now, one thing I will talk about with the bin widths, and this is actually a sore point because I read this paper where the bin widths were so wrong that you couldn't see what was going on. And so they were using bins that were just too large. So now you can see that on the left-hand side here, we have bin widths which are small. And so we have like, tiny pieces of information which appear to be scattered. You can see that it's actually not, you can see that they're not actually touching in many places here. My data is kind of like separated, they're like separated points. The bins are too small, and so they look like they're separated points. But if I make the bins too big, like I do on the right, then it makes the data look really different. It makes the data look like they're all really tightly packed into one area. But actually, that's not the reality of what's going on. And so this paper that I read, they had bin widths which were too large, and they were trying to argue at the point that certain proteins tended to cluster together based upon certain types of reactions that they were working with in their experiment. But actually, though, I wasn't convinced, not that I'm being difficult, but I wasn't convinced because I didn't know what I was convinced of. You couldn't see what was going on because the bins were just enormous. And so what they're doing is they're comparing a protein that was, in this case, it was similar to this, where a protein lands at 20. They're actually grouping that protein at x equals 20 with another protein at x equals 60 or something, which biologically you just cannot do because that's just not good science. You can't group things together so well like that. And that's totally arbitrary. There's no reason why they should group all those proteins together other than to show that their data was really flash and they had all this. I know it sounds like I'm just sore about the whole thing here, but that's really what we're trying to get. We're trying to get past as a class here. We're trying to realize that the way that you present your data actually does make a difference to how acceptable it is. Do you see something that's really there, or is it not really there? And so that is the essence of, I would say, the talents that comes from being a top-notch computer scientist. So you have to worry about the bins. And so, for instance, one of the experiments that we can try, which is actually kind of interesting, is to kind of play with the bin widths and just see, like if you have your code like this, just play with the bins and just see how the data falls when you have different sizes of bins. In other words, are you going to get a bin that's just too big where everything is grouped together like you see on the right? Or are the bins going to be just too small and give you this impression that the data is really quite discrete when maybe it isn't? So the bins are too small or the bins are too big. It's really up to you to figure out what those bin sizes should be. So one thing you can try here is, you can just go ahead and try, I'll make a new data set here. I'll just go ahead and put this in here. You can always try this. And by the way, I know that the way I'm talking about this makes it seem like there is a right and wrong answer, but actually that is your job to find out what that right answer is, because in many cases, I've said this before, in many cases, no one will know what you've seen. You are the only one anywhere who has seen this thing or has noted some trend. No one else has seen this thing before. And so it's up to you. You'll be the first person to actually see this thing. And so it's up to you to kind of work out how those bins should be placed. Now, this is a different way of working with bins. For instance, you can work with bins when you're dealing with with what's called a frequency poly or freak poly. This is a kind of a line graph. I apologize, you really can't see the yellow there, but there's a giant peak that kind of peaks up over the 0.5, I guess. But you can change the bin widths here too and kind of get an idea. So if I change this to 1, what do I get? I get something that looks like this. And if I'll just copy this so you can get an idea of what I'm looking at. By the way, this is the information, my caret data. in which the caret is less than 3. That's why it looks a bit smaller. So if I change this, if I change the bin widths around, you can see that my plot actually does look different. I wish that the colors were not yellow. That seems like such a, I couldn't have used like purple or something. I don't know. But what I'm trying to say though is that you can change your bin widths here too. And again, if I put this at let's put this at 0.7. I don't know, let's see what that does. It does change the plot slightly. But you can see that as you change the bin width here, this is this one here, as you're changing the bin width, let's say I'm looking at 0.5. Let's say my bin width here over here is 0.05. I'm looking at the bottom plot. I guess it's the purple plot. It's the very, very bottom one for the x equals caret. You can see x equals 1 here. It's like the first line that you encounter as you're going up. That is fair. So if I look at my fair, it looks like it's really, really far down to the bottom here. If I change my bin width to 0.7, you can see that now fair is picking up. It's becoming a bigger number. If I look at 1 here, fair is even bigger number. What happens if I like go just crazy and I like change this to like 10? Does that change much at all? You can see now that the data becomes very kind of triangular. And so what I'm saying is that you're kind of creating, your data now is either fitting to something which is -10 to 0 or 0 to 10. And so it becomes more and more binary. I guess it becomes, there are less categories as the numbers get bigger and bigger. And so again, this is all the same data, but I would say that looking at this and looking at this appears to look like different data. It appears that it's not the same thing. And so the message here is that as you are plotting your data when you're working with categories, please do spend some time kind of working out whether your bin widths are actually giving you a fair description of what's going on in your data sets, because you'll find that it doesn't always work out that you're looking at the right stuff. Anyway, I think I've made this point clear now. I don't need to take a while. I know you're probably thinking, what's the biggie here? Why is he keeping on with this point here? The reason why I keep talking about this though is because this is a problem that happens many, 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 many more times than it should. In fact, just last week, in fact, or the week, just about last week, I was reviewing a paper, and it was the same thing, another bin problem, where I thought to myself, actually, if the bins were more narrow, then we'd have a better idea about the distribution of these points that they're talking about. And they didn't seem to know that the bin widths actually do make a difference. But now you do. And so now you are equipped to be excellent data scientists, right? Right? Okay. Anyway, so what I'm trying to say though is this is the point here. This is the new color scheme here, blue, or the greenish blue and the yellow. And that is that the way that you present your data may help you to see more. And so the thing is though that by changing these bin widths may help you to see further, something that no one else has seen before. And remember, you are pioneers. You will be seeing things that no one else has seen before. And it's your job to make that absolutely clear, to make that observation clear, to help your community make decisions based upon your observations. Hopefully those decisions will be ethically inclined, but decisions nonetheless. And so you have to think about what's the best way of actually putting this out. These are just some more examples of using bins here. Let's see if I run this thing through. I think we may have actually run this code before. I'm not quite sure. Let's just go back and see what happens here. Let's see. So if I go back here and I run this, let me think. If I run that, yeah, okay. So if I paste this again, let's see. What if I put like 10 here? Something crazy. There we are. So well, look at that. If I put 10, everything gets lumped into one bin. And so I can say, this is my data. Can you imagine if someone comes to you and says, this is my data set, and you're like, this is just a giant gray square. This doesn't tell me anything. But you have to, I mean, it's like you have to think that that's not very helpful. Let's see if I put 5, does anything happen here? So another 5, I get a rectangle on one side, I get nothing on the other side. And so it makes a difference. You get some pretty crazy looking results, even though the data is the same. I guess you can think of in terms of like getting back to this, that your data is kind of being kind of muffled in some place, or you lose some dexterity in your data set. Anyway, I think that you'll if you play with this code for a while, you'll see what you can do with your bin widths to make things much more interesting. I'm going to, I think we've kind of finished talking about the bin widths here. There's some other examples that you can look at here. This is kind of like what we just talked about. This is the same data set, but I'm just changing the bin widths. Now, you can see that, I guess it depends on what you're trying to argue. If I'm just looking at, I mean, typically you'd have a distribution. You'd use a histogram like this to get a distribution, to see how your points are actually distributed. Where are the peaks? And I guess that if you're looking to see the peaks of your data, what I try and do is I try and use like a smaller number first. Like for instance, I have bin width of 0.1, and then I kind of go up from there. I think that this is too high. I never go above 1, although you can. It's logically possible. But in what I'm looking at though is if I'm trying to find like a distribution, I'm looking at, I don't know if you can see this, but where I am right now, just above the like maybe at 1.9, it seems like there's almost a break in my data. So I try and find a bin width which allows my whole set to still be somehow intact. In other words, if I were to put my finger on the gray plotting or the gray ink of my plot, then I should be able to get to any part of my plot without having to pick up my finger. Now, that's kind of getting almost impossible here because right above where I'm right now, right above the 2, you're almost running out of places to actually run your finger. And so that means that you're almost beginning to break up your data. And so what I'm trying to do is I'm trying to find a bin width, like for instance, maybe 0.5, where the data set doesn't get broken up. Try and find the lowest bin width so that the data doesn't get broken up. And it still seems to make sense. And so this, I would say that I would probably use bin width 0.05 to illustrate this bin width or this distribution of my data. Here's the code that you can try running and just to kind of get an idea about how all this comes together. I think that, well, I don't know how much time we have. We have like maybe 2 minutes. I think I might stop here and then we'll hit these slides when we're talking about actual different types of numbers. We'll talk about those slides on Thursday, just because we're kind of changing gears a little bit. And so what we're going to do is we'll end here, and then on Thursday I'll come back, and then we'll hit the rest of the slides, and then on Thursday I think we have some other things planned, which are going to be action-packed and ultra exciting. It's just like a non-stop roller coaster of fun in this course, right? Why is everyone so solemn? No, but still, I think that we'll end here, and then we'll come back with some other, and then we have some other things planned for Thursday, which will be fun. Are there any questions at all of everything here? I think we have like 5 minutes to go. I mean, I could, if anyone has any questions, we can go over them, but otherwise it's going to take us more than 5 minutes to look at the rest of these things here. All right? All right then. Well, yeah, okay. I think that's it then. Everybody, thank you for coming in today. I will see you all next Thursday, and everyone stay well. Alrighty, take care.